All right, McMurray 16.10, multi-step synthesis. Multi-step synthesis is one of the holy grails of organic chemistry. It teaches us a great deal about logic and reasoning and ordering of things, but it also allows us to make variants of medicines. Most medicines, in case you didn't know, are not made by physicians. Physicians merely have the legal monopoly to prescribe medicines. They're not made by pharmacists. Pharmacists merely have the legal monopoly to distribute and sell drugs. It's typically organic chemists who synthesize and make these. Now we work in large multidisciplinary teams with physicians because we need people in the clinic to treat patients with them. Organic chemists typically don't want to treat patients. We're squeamish about those things. That's why we've avoided the medical profession. You need pharmacists, pharmacognosists, and pharmacokineticists and things to understand the rates at which these things happen in the body, the rates at which they break down, because if you put it in your body and it breaks down too fast, like if it breaks down the acid in your stomach, then it never makes it into your system. That's no use. So it would have to be applied in a different way, maybe directly to the bloodstream to avoid the pH 1 hydrochloric acid in your stomach. Now, how does multi-step synthesis work? Let's take a look at a tri-substituted benzene. Okay, we need to put three substituents on this system. How do we do that? The question is, what order do we take them off? Do we take the methyl group off first in trying to think about synthesizing it, or that's called retrosynthesis, when we think about the synthesis backwards. And if you're not familiar with retrosynthesis, it's not cool 1970s synthesis like in that 70s show. It's reverse synthesis, okay? Thinking about molecules in a backward synthetic sense, what precursor came before. Now remember, when I taught you to learn reactions, I said learn the reaction forward and backwards, right? Because we need to be able to think backwards in synthesis, in developing multi-step syntheses. So we could take the methyl group off, we could take the nitro group off, or we could take the bromo group off. Okay, and we should analyze each of these pathways. Now, chemists use a funky arrow to indicate retrosynthesis. Two parallel lines like an equal sign, and then a double-headed arrow on the end of that. So let's take off A. That would give us a precursor, a new target here. All right, let's take all that away. This is not the one in the book. I have the bromine in the wrong place. All right, starting over on multi-step synthesis. All right, so we could take this molecule apart, and when we take things apart, this is called retrosynthesis. Okay, that is, we're thinking about synthesis in reverse. Remember when we were learning reactions, I said learn the reaction in the forward direction, but also learn it in the reverse direction, because this is critical for our understanding in terms of designing syntheses. So suppose this is the molecule we need to make. Well, what's the last thing we want to put on? We could put the methyl group on last. Let's call that path A as we begin to look at this. We could put the nitro group on last. We'll call that path B. Or we could put the bromine on last. We'll call that path C. Now, let's look at and conceptualize the precursors for each of these. Chemists have a funky arrow, this two parallel lines and then an arrowhead pointing backwards to indicate retrosynthesis. And it's not about reagents. You're not putting reagents over that, but you need to maybe have some in mind eventually to do the forward synthesis step. So this would be the precursor. We could imagine it though if we had a methyl cation, right? Because we learned a reaction called the Friedel-Crafts Alkylation, right? Where alkyl cations add to a ring. But Friedel-Crafts, if you recall, has a severe limitation. You cannot have strong electron withdrawing groups on it. So the Friedel-Crafts won't work. So we can eliminate that pathway. Now, notice I put this in here as the methyl. That's the retron. Okay, this is the conceptual idea for this, for the forward reaction. Now, let's consider path B. If we look at B, that would be to take off the nitro group. And of course we know how to put nitro groups on. We put them on with NO2 plus. Now, can we nitrate this system? We can. This is an ortho-para director. Methyl's an ortho-para director. Methyl's an activator. Bromine's a deactivator. So what do you think? Well, if you remember our conflict resolution rule, the stronger director, the stronger activator, the methyl group, over the deactivating bromine, will direct the nitro group, well, in the direction we want. So that step, we'd say, is viable. Okay, that's good. What about step C, or path C, if we consider this? We could take the bromine off of this para position, and if we look at our substituents now, the nitro group is a meta director, so it would direct the bromine to the desired position, but it would also direct here. But this position is much more sterically congested. This ortho or meta to nitro, which is ortho to methyl, would be more sterically congested than the alternative position. Okay. And then what about the methyl group as a director? Well, it directs ortho, can't go here, it's blocked by the nitro group, or para. So both direct to this position. So again, we would look at this and say, that looks like a fairly good pathway. So we could potentially choose either one of those. In the actual industrial setting, we would look at many things like reaction conditions, costs, and time involved, and purity of the product to produce these, and we would make a detailed evaluation of that in the industrial research laboratory before we took it up to large-scale synthesis. So this now is two potential pathways. Now how do we step back? Because this has given us a new potential, a new target molecule, if you will, if this was our original target molecule. Well, we could take bromine off of this one. I'll call that A prime, A prime. That would give us toluene. Toluene's a large-scale industrial chemical. Remember, that's paint thinner, so it's pretty cheap. The other pathway we'll call B prime. would give us bromobenzene. Now, we can evaluate these steps. Methyl, if we're going to do bromination, right, it would be Br plus is our retron here, or synthon. So we know how to brominate this, and the para position would be one of the positions we would predict. Alternatively here, this would be by Friedel-Crafts, using the methyl cation to methylate bromobenzene. Bromobenzene is deactivated relative to benzene, but it's not eliminated as a Friedel-Crafts reaction partner. That's supposed to be plus. Whereas methyl is activated. So we would expect then that the toluene bromination pathway would probably be better, and we could actually start with toluene in our synthesis. Okay. Now, how about the other one? Again, we see, maybe we can already see that if we want to take the methyl group off, we'll call that A double prime, we would be trying to do a Friedel-Crafts on a deactivated ring, and that's not going to work now. Alternatively, we could take in B double prime, the nitro group off, and again that would give us toluene plus NO2, and we know how to do the nitration chemistry. Okay, so methyl would be an ortho-para director, and there are conditions that could give us a preference for the ortho substitution. All right, I'm going to take a break and then I'll come back with the synthesis.